Hello, we are Team 7. Today we are talk about reactive control for autonomous drones. The unmanned aerial vehicle, which also known as drones, is an unmanned aircraft operated by radio remote control equipment and self-contained program control device. It can also be operated completely or intermittently autonomously by an onboard computer. The UAV are often better suited to tasks that are too dull, dirty, or dangerous than the manned aircraft. It can be used in many different areas, such as disaster relief and environmental protection. For disaster relief, unmanned aerial vehicle equipped with high-definition camera is used to take aerial photographies of affected areas, providing first-hand and up-to-date images. The unmanned aerial vehicle operates rapidly and can ensure the safety of rescue work. By aerial photography, it avoids the dangerous areas where landslides may occur. It will provide a valuable reference for the regional distribution of rescue forces, the determination of key areas for disaster relief, and the selection of safe rescue routes and the location of post-disaster reconstruction. The UAV can also monitor the situation of the affected areas in real time and in all directions in order to prevent secondary disasters. For environmental protection, it can observe the air, soil, vegetation, and water quality, and can also quickly track and monitor the development of sudden environmental pollution events in real time. In addition, the UAV with catalyst and meteorological observation is used to spray in the air to eliminate haze in a certain area. The UAV carries out aerial photography with strong persistence. It can also use far infrared night photography and other modes to realize all-weather area monitoring. Unmanned aerial vehicle is not limited by space and terrain. It has strong timeliness, good maneuverability, and a wide range of patrols. Autopilot is the core part of drones. It is a device that can automatically control the three-axis movement of an aircraft by the pilot pressing some buttons and rotating some knobs, or by the navigation equipment receiving the ground navigation signals. It can help pilots complete some auxiliary work and reduce the workload of pilots. In UAV, it can control unmanned aerial vehicle flight by receiving signal from controller. Autopilot software is very important to determine the performance of the UAV and some basic indicators. For example, low-level control will give a bad influence to the photo when using drones to take photographs. In addition, it is partly responsible for overall energy efficiency. So the lifetime of unmanned aerial vehicle is usually the result of simplified autopilot operations. Because of the gas or pressure gradient, the control logic may operate more or less frequently regardless of the fixed rate at which the execution is triggered at the corresponding time. However, the drones can only run control logic when it recognizes the need by using reactive control. It allows the autopilot to significantly improve the performance of drones in terms of motion accuracy and energy consumption.
However, it is not easy to achieve the reactive control. Three issues need to be resolved. The first one is the change of sensor input depends on several factors, including the accuracy of sensor hardware, the physical characteristic of the drone, the control logic. The second one is the indications of the operational control logic may come from different sensors at different rates. So the question is how to handle the possible interleaving. In addition, not running the control loop for too long may have a negative impact on the stability of the storm and may prevent it from returning to the correct behavior. And the third one is when implementing reactive control, the code quickly becomes callback hell because the operation itself is event-driven. As for the first issue, although the control logic is deterministic, change in the control output can be considered as random phenomenon. The input to this phenomenon is the difference between samples of the same navigation sensor. The output is the binary value indicating whether the attractor setting needs to be changed. Therefore, an accurate statistical estimate of this random phenomenon can make an informed decisions about whether to run the control loop. Among the estimators with binary correlations variables, logicity regressions, as shown in Figure 4, fits well with these situations. For small changes in sensor input, the probability of attractor setting change is small. When the change in sensor input is large, the change in attractor setting is deterministic. The second issue is about the during with time. The system's hyperperiod is calculated as the minimum time interval for all sensors to be resampled. Based on the sample frequencies of each sensor in the system, after first identifying the contradictions under which the control loop needs to be executed, it needs to wait until the current hyperperiod is completed. In addition, in order to resolve the continuous false negatives, the control loop is operated at very low frequencies. Finally, how to implementing the reactive programming is the third problem. Efficient RP implementations is achieved by relying on several key features of reactive control. First, the data dependencies graph encodes the control logic. Therefore, its layout is known as compiling time. Second, the sensors used as initial inputs are only a few. Finally, the highest frequencies of data change is known for each sensor. The highest sampling frequencies can be safely approximated. So after implementing the reactive controls, how's the performance change? The first improvement is the improvement in pitch error. It is the ability to shift processing resource in time that enables more accurate control decisions. The second one is the improvement in posture error translates into more precise motion control and less posture correlations. Therefore, energy efficiency is increased. The third one is more efficient operations in end-use applications. Performance improvements in reactive control reflect more efficient operations for end-use drone applications from 3D reconstructions to search and rescue. However, the reactive control is not a perfect process in drones. People would like to obtain a precise specifications of what kind of drone can support reactive control, but in computing terms, this essentially means a specification of the target platform. This task represents a multidisciplinary challenge in that it requires skills and expertise beyond the computing domains and retreating into electronics and mechanics. And the reactive control can also be used in other areas. For example, incorporating artificial skin signals in the constraint-based reactive control of human-robot collaborative meditation tasks. The aim of this study is to develop a collaborative meditation control strategy for robots that can process a large number of artificial skin sensor data. The artificial skin contains over 300 interconnected cells, and robots and operators interact in a shared workspace to accomplish industrial tasks. The robot controllers detect and avoid collisions based on information from artificial skins in order to reduce the amount of data. The discrete optimization algorithm selects the maximum number of cells according to the single intensity and spatial distribution of activated cells. And the other example is vision-based for sensitive reactive control for a quad vehicle. The air robots are deployed to perform tasks such as door-to-door delivery and close area inspection. Robots are required to travel through complex and disorderly 3D environments such as forests, garages, and shacks. However, classical reactive control is not look ahead, but tends to rebound from obstacles rather than generate a small trajectory to predict and avoid impending obstacles. But this study derives a complete image-based control standard, which predicts the free space cylinder falls into the image stream representation of the environment and controls the vehicle by manipulating the cylinder in the upcoming environment. And third example is reactive control technology for 3D navigation of non-holonomic robots in tunnel-like environments based on limited sensory data. A constant velocity non-holonomic robot should pass through an unstructured and unknown 3D dimension tunnel-like cave environment. The sensor provides information about nearest point on the tunnel surface and the distance from any light emitted by the robot to the surface at an up angle reactive to the nearest point. A new navigation law is proposed which respects to the given safety margin on the robot surface, drives the robot to a predetermined distance and keeps the distance. This law generates control as a reflective response to current observation. A strict mathematical proof of this law is made, and its applicability is verified by a computer simulation test. And here is our references. Thank you so much.